is running. Okay, combination circuit is basically when you have a series and a parallel combined, aka also known as a network. So when you have a network, you're talking about a combination circuit. Okay, so the best way to actually analyze a combination circuit is to go right into an example. So I'm going to call this example 1. Okay, so I'm going to draw a combination circuit here. Okay, let's take it easy and just do a simpler one for now. Okay, so what kind of circuit do you have here? You know it's combination because we're talking about combination circuit. All right, so what is happening, right? So I'm going to call this R1, R2, R3, and R4, and that pen is dead. Okay, yeah, let's make this 5 ohms. Let's make this 10, 15, and 20. How predictable. Okay, let's make this 120 volts. Deal with 120 volts here. All right. When you're analyzing, you look at what's going on here, right? So current's gonna come out of here. So there's your IT, total current. Okay, it's gonna hit this junction right there. What do we have? What can we say about R3 and R4? I'm gonna go this way. Some of that current's gonna go that way. You got a junction. Are these two in series or in parallel?
Parallel.
R3 and R4.
Parallel.
R3 and R4 are in parallel with each other. How do we know that? See this junction right here? You got two choices, right? You can either go down and power up R3, or you can go that way to power R4, because your goal is what? You gotta get back to the power source at the end of that cycle. That cycle has to be completed. It has to go back this way, and it has 2 different roads, right? So now here's what's happening. Current's gonna go through R3 and then R2 and R2 and R1 and then back to the power source. The other one, R4, doesn't have to go through R3. That's why they're in parallel. But R4 has to go through R2 and R1. What can we say about R1 and R2? Are in series with each other. Okay? But we also can say that R3 is in series with R1 and R2. Because look, R3 has to go through R1 and R2. These guys are in series. But R4 is also in series with R2 and R1. So what would be the best way to do this is how to deal with a combination circuit, how to do the analysis. We call this circuit analysis. Is step 1, you need to simplify the circuit first. How do we simplify? Now, in the math class, when we say simplify this equation, what do? How do we simplify an equation? We combine the like terms, right? So if you have 1x plus 2x plus z, what do? You combine the two that are x, right? 1x plus 2x becomes 3x. So here you can simplify the ones that are the same. So R3 and R4, the first thing you want to do is simplify these two. So here we can then find the equivalent resistance. So we're looking for the total resistance. This is called the equivalent resistance. R equivalent, equivalence. Okay, the equivalence resistance is not the total yet, but the total of the parts of the circuit. So we can find the R equivalence of these first. That's simplifying, right? So that's always your step 1. Step 1 is to simplify. And then step 2 will be to analyze. What do they have that's the same, right? Analyze what is the same Is it the current or is it the volts? Right? Using Kirchhoff's rules. And then 3, you're going to analyze the individual ones. The individual I and the individual V. Okay, so basically those are the 3 steps. So we're going to go through those 3 steps as we analyze this circuit. Okay, so step 1, let's simplify what we can. So I'm going to combine these two first. Okay, so R3 and R4 will be the first one I do. So how do we find the total resistance of this? I'm going to give you 30 seconds to give me the total resistance of R3 and R4. Go.
85.
Go. Get your calculator and actually do it. I'm not going to do this for you because at this point you know how to do this.
15. It's just 15.
Okay, this is parallel.
What is the total resistance of these two, R3 and R4?
Yeah,
How do you do that?
Yeah, 1 over 35.
1 over.
1 over the R. Okay, I'm going to call it the R equivalent because that's not the total yet. 1 over 15 plus 1 over 20. Can you get me the equivalent resistance, please? Remember, we try to save time. So what you want to do then is use the calculator. Go 1 over X right there. Use that one. So I'm going to go 15. This. Yeah? That what you got?
6.5, right?
The answer is 8 point. Let's do 2 decimal place. Do not round off. Okay? With electricity, you got to use at least 2 decimal place. So this is going to be 8.57 ohms. So we're in the simplification here, simplifying it. So here's what I'm going to do now. Because I simplified it, I'm going to simplify my picture as well. This is now what we have. All right, are you guys okay with this one? R equivalent for now. We're good, right? So here is what we have right now. So I still have my R1. I still have the R2. But look what we've done here. This is now just 1. I've simplified. This is now the R3 and R4. I've combined them. So you still have your R1. You still have your R2. R1 is still 5 ohms. R2 is still 10 ohms. But what is R3 and R4 combined? 8.57 ohms. We have made it into one single resistor, right? So now, I want you to find the RT. Can you now find the RT of these resistors?
Yeah.
Now it's easy, right? Now it's easy. All you need to do then is, because they are now all in series,
3.57.
so it's 5 plus 10 plus 8.57, which is 23.57 ohms. That is the total resistance of this circuit. So we've done that. Remember, when you're analyzing the circuit, you're always looking for these things. Always, always. When you're looking at any circuit, you're looking for what is the VT, what is the RT, what is the IT. You may need to know what is the PT, the power as well. And then you need to be able to find the individual ones. Okay? So right now, we have just knocked off the RT. Done. We've done that one. So I'm going to put a check mark on that. So in our circuit analysis, you got to do all those things. Sometimes you may even find the cost. What is the cost? Well, we kind of did one question yesterday, right? Or the day before. Okay, so we know the RT. Do we know the VT? Hang on. We know the VT because it's given 120 volts, right?
Yeah.
So that's done. Can we now find the IT?
Yeah.
You can. Now, before we get there, what's the question?
So when you're looking for VT, are you gonna do it when they're combined, or are you gonna do it when?
Well, what does VT mean?
Total.
Total.
Yeah, total.
So if you're looking for the total volts or the total I or whatever total that is, it's got to be total of everything.
Yeah, but when they're together, are you gonna take it from there?
Yeah, That's
all get into one.
if you're looking at the total, you have to use the total resistance. But when you get into the individual ones, you'll have to go back to the original picture and look at the individual R. Yeah. Okay, so we have the VT, we now have the RT. Let's calculate the IT. So how do we find the IT? I'm going to give you 10 seconds to do that. Go.
The total IT
Mm-hmm.
series it will be the same. This series.
Well, yes, but we don't know what that is. I need you to calculate it for me.
Okay, yeah.
So remember, V equals IR. Okay, so I will be VT over RT.
5.09.
So 120 volts divided by 23.57 ohms is 5.09 amps. That's the current. Done. So we have now the total current as well. So I'm going to check that in our circuit analysis. We're getting there. Total current. Can we calculate the total power now?
Yeah.
Yes. Okay. So total power P equals IV. Because we're looking at total, everything has to be total. So far, pretty easy, right? Okay, so I is 5.09 amps. The volts is 120 volts. Can you get your calculator and give this number to me, please? 610.94 watts. Okay, so we have the total power. Okay, now we're getting into the individual ones, which can be the tricky part. Okay, we okay? Any questions so far with the total? That's the total power.
No, total current. It will be.
That's the total current, right?
It will be individual current. It will be the same, right?
Hang on, before we get to the individual ones, is this crystal clear?
Yes.
We're good? I need to make sure you guys understood what we just did here. We're okay? Because we're just looking at the total. Now let's look at the individual ones. Okay, so I'm gonna keep in mind that this is the original drawing. So the individual analysis of the current and power and volts. So the individual resistance now, right? So the individual resistors, we're gonna isolate those. All right, so let's take a look. Keep in mind the IT. What was our IT? 5.09. That's the total current, right? Okay, so because what do we have in series? Let's go back to the simplified diagram right here, right there. Remember, these are all in series with each other. If we're getting 5.09 amps coming out of here, how much will this get in terms of amps? The same. Good, the same, because they're in series. What is the same? Analyze what is the same. Step 2 now. We're in step 2. What is the same in this case? Because this is in series, the same current for all of them. So that means this together we'll get 5.09 amps. This is gonna get 5.09 amps. This is gonna get 5.09 amps. Okay, so I'm just gonna write down what we know so far. What is our I1? 5.09 amps, right? I1 is R1. R1 is a resistor. The current in R1 is I1.
They're all same though.
What is I2? 5.09 amps. Now, what is I3? No, we don't know.
I'm sorry. Okay.
It's half of 5.9.
It's I3 and I4 combined that gets 5.09 amps, right?
So you have to
But because they're not the same resistance, if they're the same, if this is 15 and 15 and 20 and 20, just divide it. They'll split it evenly. But they're not the same.
Because
So we
it's
need,
parallel.
because they're in parallel, the current is going to be different, right? And so we need to calculate that. So going back to Ohm's law, V equals IR. What's the formula for I? V over R, right? So how do you calculate I3? Using this formula, you're going to go V3 over R3. Same thing with I4. You're going to go V4 over R4. Okay? Yeah, thanks. Okay, now the question now becomes, what about the volts? We don't know the volts just yet. We can't do this yet because we need to know the volts. So that's the current. Let's take a look at voltage now. Okay, so we're looking at V1, V2, V3, and V4. Okay, so we now know the current, right? For I1, I2. How do we calculate the V? IR. Right? Can we now use Ohm's law to just calculate the V1? Do we know I1? Yes, we do. It's 5.09. Remember? It's the same.
Yeah.
We just figured that out. And what is the R? 5, isn't it?
Yeah.
Now we know the volts. Because remember, in series, the voltage will be different from the total one. So what's 5.09 times 5? 25 point something, right? So let's keep it in 2 decimal place. 25.45 volts. So we know the volts for V1. What about V2?
Basically double.
5.01 times that time or something.
Well, it will be now I2 R2. So 5.09 amps. It will be exactly double because this is 10 ohms. So what did we get?
50.9.
50.90 volts. So far so good? It has, go back to the original diagram here. See, because it has 10 ohms, it's fighting more. You need to give it more kick. The volts is the kick. This is the hard part. How do we get the V?
Now it will be.
This is the hardest part.
Is
This,
it parallel?
I gotta get, yes, it's in parallel.
It's the same time.
That will be the same, right? These two are in parallel. They will have the same voltage. But how do you know what voltage will they be the same?
So we didn't give it the same voltage.
Let's take a look at VT. What is the VT?
120.
120.
Oh, you remove both, then divide by 2.
You got it.
Yeah.
So here, take a the divide it by 2. Hold on to that one for a second there. That's wrong. Okay.
Oh, no. Okay, never
No,
mind. Yeah.
voltage.
Yeah.
They give me 120, right?
120 is the whole thing,
Yeah.
right? So here's what happens. The volts, okay? The R1 is going to take 25.45 volts.
Show the picture of the first one.
V2 is going to take 50.90 volts. How much volts together? Yeah? How many? How much? Together, they will be 76.35 volts. Well, because V1 is 25.45, V2 is using up 50.9. Together, they're using up 76.35 volts.
Okay.
So, but you're giving it a total of 120 volts. So how many volts are left over? Remember how many volts go through before it goes back to the power source? How many volts are you supposed to get?
You need to subtract from 120.
How many? Okay, you start with 120 volts. Some of the volts are getting used up. How many volts will be returning right here? 0. Good. That's a concept that we need to know that by now. So if you're using up 76.35 and I'm going to give you $120, for example, Adam, here you go. I'm giving you $120. Okay? How much do you give me back?
The rest.
0. When you come back to me, it will be 0. You have to spend it all. Wouldn't you like that, right? You get an allowance from the bank, all right? Spend it all and you don't have to pay me back. That's what it is in a circuit. I give you 120 volts. When you come back to me, it's gotta be 0. It's better be 0. Better be. So what you're gonna do then is you're gonna subtract that 76.35 volts, and whatever is left over is gonna be used up by V3 and V4, which is how many volts? 43.65 volts left over. But because this is the leftover volts, how much would each one take?
You divide by 2.
Was the same.
So this is going to be 43.65 volts. This is going to be 43.65 volts. That's the hardest part here, because just just because you have that much and you have two doesn't mean you have to split the money. You don't. Because in a parallel circuit, they get the same volts. So whatever's left over is going to be kicked into them, because you know what? They don't need to split it because it's a different road right here. So that 43.65 is going to be taken by this, but it's also going to be taken by that because it's a separate path. Does that make sense? All right. So we have just analyzed the individual volts right here, done. Then we can go back and analyze the individual current. Okay, so V3, you now have 43.65 divided by, what is our R3? 15. Okay, that will give you the I3. And this one here is 43.65 divided by 20, and that will give you the I4. Okay, let's just put in the numbers and let's analyze what they mean. 2.91 amps, and this one here is what you get? 2.18 amps. Okay, so let's take a look here. When you combine these two, these are in parallel. What happens when they are in parallel? What happens to the current? Is it different or the same? Different. If you combine these two, 2.91 plus 2.18, how much are you supposed to get? Well, how much do you get? Go ahead, add it up.
You get the total.
You should get 5.09 amps. And do you? You do.
Why though?
Well, because that's the current. The current splits. You see here? The current, you see that current? I just drew it right here. Junction. This is called a junction. The current, some of the current will go here. That's called I3. And some of the current will go here. That's called I4. But you have no choice here. All the current that's going to go here, that's 5.09, is going to go through R2. And it's all going to go through R1.
Okay.
But here they split. That's why it's less.
Okay, so in parallel, the total current is equal to
The total current. Yeah, the total of these two individual
Equal to the
ones
total.
in a parallel circuit is equal to the total current of the whole thing. So we've just analyzed all the individual current and all the individual volts, and we're done. That is the analysis of this circuit right there.
In the parallel, we say we have the same voltage, right?